Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So really today what we're going to talk about now are what does it take that's unique about designing parts for spacecraft. And really this is over and above the failure mechanisms that we spoke about last time of multi-packaging and corona failure. And really today we're going to focus on some other special design configurations, some unique reliability requirements that spacecrafts require. And then we're going to go into a few applications and TRM differentiators, and then we'll sum it up at the end.
Okay, well, thank you. And we noted a moment ago, and you've talked about it before, that an end user's environment profile is a big impact on the design for space applications. Can you add a little bit more about the environment?
Sure. Spacecraft offer a very unique environment, and that is that the parts are in a vacuum. So what does that mean? It means that there's no air pressure or any pressure at all in and around the part. Now, most spacecraft, because they don't want to come up with a unequal pressure around a lot of the parts, they actually want us to vent the parts so that the parts can breathe. By allowing the parts to breathe, that makes sure that there's no internal stresses on the housing or the other mechanics of the parts, since the pressure on both sides of the housing is equal, just as if it would be down at sea level. Now, what's unique about that when you operate in a vacuum is there are certain things about the materials and behavior materials that really you don't think too much about when you're doing stuff that is not in a vacuum, and most of that has to do with material outgassing. Material outgassing is a phenomena that is something I'm going to talk about in a little bit more detail in a minute. But it is a parameter that's critical for spacecraft, and we're going to go into a little bit why. Related to that, also, there's different material finishes that are also very, very critical for parts on spacecraft. Also, the environment being in outer space without having the ozone layer to protect it is that the radiation level from the sun can be quite significant, and radiation can adversely affect many materials, really shortening the material life. The next thing I think that really drives this is reliability. We all know that it's very difficult to do a service call on a part if it's on a spacecraft, and therefore designing parts for the utmost reliability is of paramount importance.
Well, that makes good sense. Maybe you could share a little bit more information then on outgassing.
Okay, so outgassing is one of those things that, like I said, most people don't really think about. But what it is essentially is, and almost all materials do it. Basically, if the material smells, it means it's outgassing. That new car smell that you get are all the adhesives and glues and everything else in the car, outgassing. And creates those sorts of odors. But what outgassing really is, it's a measure of how much material is released as a gas when exposed to a vacuum. As soon as you relieve that air pressure right on the outside of a part, anything that is not molecularly really tied into the material can then leave the material. And in a low G environment, you actually lose weight of the material. Materials actually get lighter. NASA established two different criteria that they when they talk about to quantify outgassing. One is TML, or total mass loss, and in order for a part to meet the NASA outgassing requirement, you have to lose less than 1% of its total mass due to outgassing. The second criteria, which is actually almost more important than the total mass loss, is the CVCM, or collected volatile condensed material ratio. That has to be less than 1%, 0.1%, excuse me. And what that is that how much of that material that actually that expands and you lose from the material, how much of that material will actually recondense and become a solid, displaced someplace else. And this is a requirement that is across the board, used on spacecrafts. And we're going to talk a little bit here as to why it's specifically important. But it is a criteria that is critical. It does limit the number of the types of components that we can use on a spacecraft. There are certain epoxies, especially other sort of materials like that certainly are that do outgas, and we have to be careful about those.
Okay, now the second bullet in that section relative to materials referenced the finishes, the material finish. Can you talk a little bit about the finishes?
Sure. Material finishes are again, there are certain things in low G environments that are much more critical than what you would see down at sea level. Whisker growth is a phenomenon that can happen down at sea level and also with higher G levels. However, in a low G environment, whisker growth is something that can and does happen much more often. What whisker growth is that if you have a finish, and pure tin is a good example of this, and there is an electric field present, the molecules of the tin and other materials do this as well, but they begin to migrate along the surface, and they actually begin to build a bridge that follows the electric field. So ultimately what happens is you end up with something that looks like literally looks like a whisker, because it's a very, very narrow, very, very fine line. And ultimately, if let to grow, it will short out some components because it will follow the E field, and it will actually cause a short circuit over time. Like I said, in a down at more sea level, at high G levels, whiskers don't grow as readily, nor do they grow as long. But in space, they grow very readily, and they can get quite long because gravity is not there to break them. And as a result, they're much more of an issue in space than what they are terrestrially. The next big item really we'll talk about on spacecraft are FOD, or foreign object debris. Material that is not connected to anything and that can allow it to move around can cause problems. It can cause short circuits. It can get in areas where we don't want it to go. Therefore, cleanliness for these space parts to make sure that there is no foreign objects on or anywhere near the circuit or the component itself is really an important matter for spacecraft. And again, that's something that we mitigate through additional cleaning cycles and inspections for that. The other thing also that's really from a surface finish condition, which we really don't think about, is the fact that where does the heat go? Now, on a spacecraft, you can't radiate because there's no air, there's no contact with the components for it to have energy radiate from the part off and to remove some of that excess heat. All of the heat has to be transferred through conduction, which means that anything that's generating heat has to have a physical path through a solid material to get the heat out of the component and onto the larger heat sink. Therefore, heat management and how the heat flows is one of those things that we really have to be very, very careful about when designing our parts for spacecraft.
Okay, and maybe you could tell us a little bit more about the effects of radiation.
Yeah, radiation is one of those things that really can be a problem. Um, Again, we don't think about it very much. We have our lovely atmosphere over our heads to protect us from the sun's radiation, unless you're getting a sunburn somewhere. But at very high levels, once you get up into space, those radiation levels are quite significant. And there are certain materials, Teflon, which is a very common material for our products, is very susceptible to radiation. Um, and basically, what happens is that with radiation, if Teflon gets exposed to radiation, it very quickly turns it into a white powder, and then it no longer behaves like Teflon. So if you're using it as a standoff or any kind of a dielectric, those dielectrics very quickly break down in a high radiation environment. Now, that can be mitigated really quite effectively by making sure that there's enough shielding around the Teflon to make sure that the radiation doesn't hit the Teflon directly. These are things that we look at as far as cover thicknesses, other housing thicknesses, other things are around the Teflon to make sure, though, that the radiation actually doesn't reach the Teflon. Also, where it's mounted on the spacecraft also makes a big difference as to how much shielding we have to have around the parts, because it's the total amount of shielding that individual component will see, as opposed to just the shielding within each individual little component. So, for example, if a component is buried deep in the middle of the satellite, you need very little shielding in place to make sure that the Teflon holds up over time. But if it's out on the edge of the satellite, or out say right behind an array, an antenna array, or out mounted on some sort of an arm somewhere, then you need much more shielding to be in place to make sure that the Teflon doesn't break down over time.
Got it. Okay. Now, the importance of reliability has come up a few times, and obviously you said, gee, it's tough to bring equipment back from space to correct problems, but I have a feeling there might be a little bit more to it than just that. Can you talk more about the importance of reliability?
Sure. So single point failure mitigation is something that all of our customers always speak to us about. The single most common failure on almost any product is the interconnections or the solder joints. So what our customers do is they require us, in order to bring the mean time between failure or MTBF numbers much better, is they ask us to have multiple redundant connections. That has to do with whether it's a redundant solder joint, making sure that the layout, for example, if we're going to use a play-through hole as a via for PCB, to make sure that there are several of them. This way, if one section of the board begins to be damaged or start to degrade over time or delaminate, there will still be a connection. One thing that we do very often is we rely on a solder joint, and then we also have either multiple solder joints, or in addition to that, we'll go in there and we'll have a mechanical compression, which it also makes the joint as well. So that actually, if the solder joint was to fail, there would still be a mechanical contact, very much like a pressure switch, making the additional contact. If we are doing very low frequency components, and we have wire wound transformers, we double wind all the transformers. And also, as part of the rest of the design is concerned, we see that if a component does fail or will fail, very often we'll use two of them in parallel, depending on the exact failure mode of that particular component, to go in there and say, okay, well, if a solder joint fails, at least the part will continue to function. It might not be totally spec compliant, but the part will still continue to function. And really, the functionality of these parts are really what's most critical for the mission. A lot of the parts that we build for spacecraft are part of the local oscillator signal distribution networks. And if you lose the local oscillator, you lose the entire bank for up and down converters. So this is mission critical type parts. We have to make sure that that signal continues to be distributed. If the return loss gets a little worse, or if we were having the insertion loss happens to change a little bit, that's a much better scenario than having it fail altogether. And that is something that we always work out with our customers to see really what parameter is most important, and we go in there with multiple redundancies to make sure that we make sure the part always functions the way the customer needs in their final application.
You've spoken as well about the impact of shock and vibration. Could you clarify a bit further on those?
Sure. The ride to space is a rough one. There's a lot of vibration on the satellites. These are very large rockets that are going up on there, and especially if the component is mounted close to where different sections of the satellite are. Excuse me, with different sections of the rocket, with those mating, where they decouple between the sections, they actually have explosive rings on there to actually decouple the sections. So it's really pyrotechnic levels of shock and vibration that these components have to see on their way to space. Once they're in space, then it's a very smooth ride, but getting there can be very rough. So what we do is we go through some very detailed analysis to make sure that we ensure that the parts will not be damaged for these very high levels of vibration and shock. We do things like encapsulate components. We design our structures so that they're mechanically stiff to reduce to increase the first natural resonant frequency, therefore reducing stresses and strains of the solder joints. Also making sure that the mounting provisions are heavy enough to make sure that we really have that we're not mechanically stressing any of the mounts going through there. So a lot of work is involved here, very critical. It's not just a matter of going through and making sure that the parts look good and work good electrically. They have to survive the trip to space, which is very often quite a critical part of the entire operation.
So these rough rides, as you put them, must be very interesting to work on. Maybe you could outline some of the typical space applications for which TRM customizes components.
Sure. Really, and I mentioned just a few minutes ago, we do a lot of work with a local oscillator signal distribution. Very often, there are master oscillators on satellites that control the up and down conversion for the various channels. And very often, if you have multiple, I'm going to use the word multiple redundant, which is redundant in and of itself, but that is a term that they use for spacecraft for these devices. Many spacecraft have 3 master oscillators. They only use them one at a time, but this way, if one fails, they turn the second one on. If the second one fails, they turn the third one on. What they require are in order, they have to distribute these signals out between these various backup systems out to the same networks. So what we do a lot of are multiple input, multiple output power dividers / combiners to service these needs. The unit that's up on the top of this graphic here, you see the 2 connectors on the bottom and the 3 connectors on the top. This is an example of a local oscillator signal distribution network where we had 2 local oscillators and 3 outputs. The long skinny unit that's down in the middle of the page, I will say that unit is quite large. It was 14 by 27 inches long. That one there had 2 inputs and 32 outputs. For 2 master oscillators, one at S band, one at X band, going out to 32 individual up and down converters. So some very large frequency conversion going on there. We use quite a bit of our parts are also used for telemetry. The spacecraft has to know where it's going, and there are control signals that are sent between the spacecraft and ground command to make sure that it's tracking where it should be going. TRM builds a variety of parts that are used for those telemetry sort of applications. We build some antenna feed networks that are again used to steer some geosynchronous arrays, as well as mode forming networks, again, for sort of tracking stuff on the launch vehicle to make sure that the vehicle is going really where it needs to go. Very exciting stuff, and very mission critical sort of applications. Again, we've also done work with anything really where the signal has to be distributed around the satellite. I think at this point, I think TRM has built parts in order that enable us to be able to do that. As of now, I know we are well over 150 different designs flying on spacecraft. We've got a lot of experience in doing this. We've been doing this since 1999. So we have a lot of experience in going through and working with all these various applications.
And along the lines of experience, maybe you could share some of the innovations or design enhancements that TRM typically has to make to these components in order to make them fit each application.
Sure. You know, each unique application brings with it a unique problem set, and I think what's so important about these sort of applications is that each one is unique to the application. There is no real common sort of space sort of customer as far as that goes. I mean, there are similarities between them, but then again, when you get right down to the details, it depends. For example, mechanically, it depends very much on where on the spacecraft it's located, as to how smooth a ride it's going to get going up at launch. Also, where it's going to be mounted on the spacecraft. You know, is it on a hot spot of the spacecraft? Is it on a cold spot? You know, what sort of thermal environment is it going to see, and what sort of mechanical interface is it going to have with its next higher assembly? And really, you know, and I think also we always go in there and we take a look at what the material that we're going through there, so we don't have any outgassing problems, any other sort of radiation problems with materials and with the material selection itself, whisker growth, all these sort of items that I touched on earlier. And I think the other part I think that's important there is, you know, not to forget our discussion from last time about multi-paction corona. Multi-paction corona is a very real phenomenon. It can happen at very low voltages in a vacuum, and therefore virtually every design has to be cognizant of the fact that this phenomena can happen, and it will happen if you're not careful. I think the one thing I also want to bring up a little bit here. Actually, I'll wait for the next slide for that one.
Well, okay, Shaun, and I think we're going to have time to address at least one or two questions, but before we do, maybe you'd like to summarize.
Yep, and I said that's about where I was. That's where I was headed, Paul, without the slides. So, you know, I think the summary here is that, you know, spacecrafts present very unique sort of applications of and requirements, really, as far as what we need. For example, outgassing. You know, I spoke a little bit about what outgassing was. I didn't really say why it's important. So why is outgassing really so important on a spacecraft? Well, if material is leaving a device and it is going to recollect, or those collected volatiles are going to resettle someplace else, they're going to settle someplace else on the satellite. And the last place that you want to have dust settling is on the lens of your very expensive camera or other sensor that you have on the satellite. And really, and what they actually do, if you do have some high outgassing material on the satellite, is it fogs the lens, and then therefore makes it very difficult for you to get good data, and very often either make, you know, cameras and optics really almost useless because they get fuzzy, or they can also go in there and they can damage some other microelectronics that are on the satellite as well. So that's why, you know, outgassing, for example, is really as important as it is. You know, some of the other sort of parameters, such as whiskers and radiation effects, are much more obvious. But, you know, it's, you know, we should not necessarily think that some of these other requirements are they're a pain in the neck. No, in reality, they're important, and there's a reason why these requirements exist. We have to go through. We have to take a look at multi-faction corona. Again, it's a failure mode. That is not something we're not used to seeing at sea level. So these are the sorts of things we have to pay special attention to. And in summary, basically, this is something that we have been doing for a very long time here at TRM, and therefore we're well experienced in it, and we know what to look for in designs. Like I said, with as many designs as we have done, I want to say that we've seen a good number of these possibilities, and I think we're ready to mount those challenges.
Okay, well, great. And I'd like to add that once again, I think you did a very nice job of explaining how TRM leverages that experience and explaining some of the engineering enhancements that are necessary to make sure that the components are not only suitable for space, but that they live up to each or can deal with each customer's environmental profile. So we do have one very interesting question that I thought I would like to pose. And it's a phrase that I had not heard before, but the question is that a commonly used phrase when it comes to designing parts for space is that the paper weighs more than the parts. So can you explain what that means?
Yeah, sure. That's something you hear a lot about in the industry, Paul. And really, what it comes down to is this: is that the space industry is extremely conservative. And basically, all that they're saying there is that they'd like to see all of the things we've been speaking about. They like to see the report. Basically, they want detailed analysis for all these environments, and they like to see the report backing up that yes, the part will be compliant. It's not so much a matter of they don't believe us. It's more of a fact of is they want to have that documentation backed up. So this way here, when they get their customer review and they ask, well, did you think about this? They can say, yes, we have, and here's the report. It's not a negative thing about the space people, like I said, but they're extremely conservative. They're happy to pay for these reports because they're required as part of the system, and we're happy to supply them as well. So it all comes out of overall safety and insurance that the components will deliver the performance that they need over their lifetime.
Well, wonderful. And why don't we just at this point say that any additional questions will be addressed through email as we're getting a little tight on time. We'd like to thank everybody once again for joining us today. If you are a customer and you would like to ask more questions or discuss more details about space applications, you can see the engineering hotline number here on the screen. It's 888-677-6877. We would love to hear from you. Obviously, there's no cost associated with these conversations. If you're one of our field sales representatives, then you know that your calls are always welcome too, and that you can submit questions directly through your CAM or through the sales portal. And for those of you that are thinking ahead, the next Tech Talk will be on Tuesday, June 22nd, also at 11 a.m. Eastern, and the topic will be applications for missile systems. Shaun, as always, thank you much, and thank you again to everyone.
Thank you, Paul.